Hello and welcome to Oxidation Reduction in Electrochemical Cells, Chapter Read Along Part 2 for the Berkeley Review General Chemistry books. I'm assuming you sat through one, but just in case you didn't, my name's Todd Bennett. I'm the author of the General Chemistry, Organic Chemistry, and Physics books at Berkeley Review. This video is designed to supplement as you read through, so please have the book open and next to you. I plan to go over examples 4.4, 4.5, 4.6, 4.7, and then the big picture of how you balance redox reactions. And so this is more of an application. So in part one, we went over how to determine oxidation states, how to identify reducing agents, oxidizing agents, seeing them in context, apply them to things outside of GChem. This one's probably going to be more GChem centric. And I want to transition this particular time into test perspective, test logic. Because at the end of the day, what you're trying to do in going through these books is become a better test taker. And so it's too easy to get caught up in absorbing material, trying to memorize a bunch of words. That's what so many people focus on. My personal opinion is there's way too much Anki going on. People mistakenly think the more you know content-wise in terms of terminology, the better you do. And while it's true to a certain point, if you know nothing, you're in trouble, there becomes a point of diminishing returns. It's not about memorizing, it's about applying. And then learning how to recognize what they're looking for in questions. I'm going to focus more and more with each section, each part in this on that. So I want to go ahead and start. Identifying a redox reaction, just picking up where we left off, you need to recognize that a species has been oxidized, a species has been reduced, which is the reducing agent. That's where we left off last time. So in this case, I want you to just remember oxidizing agents get reduced, reducing agents get oxidized. So it's got to be a reactant, so we're down to either calcium or HBr, and I need to consider oxidation states. So any element by itself will carry whatever charge. So whatever the formal charge is, that's also its oxidation state. In this case, calcium is a neutral metal by itself. It's going to be a 0. Hydrogen, we're going to look at it in the end. Molecular hydrogen, charge is 0, also oxidation state of 0. But then we need to consider what happens to the rest when it reacts. So bromide is a -1. It's a spectator ion in this case. So if bromides are -1 each, there's 2 of them. And the product calcium bromide, calcium must carry a +2 charge. Probably not a big surprise considering it's an alkaline earth metal, and that column takes on a +2. And then HBr, hydrobromic acid, hopefully you're aware that H is +1, bromide's -1. Acid's not a big surprise. Bromine, you'll notice, doesn't change its oxidation state, remains at -1 the entire time, so it's a spectator ion. Calcium's getting oxidized, hydrogen's getting reduced. So because calcium is getting oxidized, it is the reducing agent, if you were asked. Because H plus is getting reduced, HBr is your oxidizing agent. So oxidizing agents get reduced, reducing agents get oxidized. Okay, so good idea to know that, just the terminology. Hang on to these thoughts because that's a reasonable question for them to ask along the way. But it leads into the concept of balancing. That's going to be one of the steps, identifying the oxidation half reaction, reduction half reaction, identify how the oxidation state change. That's how you're going to start the balancing process. So everything we've done so far is to build up to this. If you recall from general chemistry, you probably spent a half page of paper and quite a few minutes balancing something from scratch. They either had you do the half cell method where you split it into 2 half reactions, balance the 2 independently, add it back together for the overall balanced reaction. There's also the bridge method. That's the one I'm going to emphasize. But I want to take a sojourn in a moment into test logic. The MCAT, you get on average about a minute per question. So you cannot afford to do the traditional method you learn in GChem, OChem, physics, biology. You have to be quicker and reason faster. And so I'm going to show a 5-step process that please do not focus on the overall 5. Focus on the individual steps and which ones you would actually need to answer certain types of questions. So if they give you a question where they ask what is the ratio of the oxidant to reductant, or how many reduced molecules will be formed compared to oxidized molecules, some ratio like that, you can solve it just doing the first 3 of the 5 steps we'll discuss. If they ask for exact coefficients and a perfectly balanced equation, because it's multiple choice, you can make your life easier by actually going backwards. Look at the answer choices and do the 5 steps I'm going to cover here in reverse order. And I guarantee you will never need to do more than 3 steps to answer any of their questions. Hopefully you can get it done in 2 in some cases. So with that in mind, here's the 5-step process. So we're asking, like, what are the stoichiometric coefficients for each of the following in this reaction? And so there's a couple molecules that are not listed there. That's typical. You're going to have water to balance out H's. You're going to have to add either acid or base. I'm going to say that let's do this in base. A question can assign it either way. I've chosen base because there's hydroxides in it. Hydroxides will be more prevalent in a basic environment. So we have to go ahead and start. First step, identify the oxidation states of everything involved. O's and H's should be your obvious ones in pretty much most molecules. Occasionally there'll be something like a peroxide or an O2 you have to worry about, but by and large they're fairly straightforward. So you're going to look at the other elements and get those by default. So starting with VO plus, O is a -2, but because the net charge is +1, vanadium has to start out at a +3. In cobalt hydroxide, you have 3 hydroxides. I'm going to look at those collectively. Hydroxides -1, 3 of them -1 means cobalt starts at +3. Vanadium in the product, there's 3 oxygens at -2 each for -6, but because it's overall -1 charge, the oxidation state of vanadium is +5, and then in the end, an element by itself, always its oxidation state is the charge, no charge, so 0 oxidation state. Okay, so I've identified the oxidation states of the key players, and vanadium I see is going from +3 to +5. It's been oxidized. Cobalt's going from +3 down to 0. It has been reduced. Okay, so second step, identify those half reactions. Just did it verbally, but let's go ahead and draw it in. Specifically, the vanadium species is being oxidized by 2 electrons. It's lost 2 electrons. The cobalt species has been reduced by 3 electrons. So half reactions are oxidized by 2 for vanadium, reduced by 3. So those 2 steps should go reasonably quickly. You've been doing those in this chapter so far. Hopefully that's nice and straightforward. Balancing entails making sure you have the same number of electrons in the oxidation half reaction as you do in the reduction half reaction. It also involves making sure you have the same net charge on each side of the reaction and make sure your atoms are balanced. So we're going to do it sequentially: electrons, charges, atoms. For electrons, all the electrons lost in oxidation are picked up by reduction. Clearly 2 does not equal 3, so we balance this out by cross-multiplying. So if we have 3 of the oxidation reactions and 2 of the reduction half reactions, then 3 times 2 equals 2 times 3. So easiest way to do that, take the number of electrons in a given half reaction. Let's just say we look at the reduction, that 3. That 3 becomes the coefficient in the other reaction. So take that 3, move it down, take the 2 electrons in oxidation and move it up. So we have 2 times 3 for 6 electrons associated with 2 of those half reactions, and 3 times 2 for 6 electrons associated with 3 of that oxidation half reaction. So those numbers we just multiplied by, the 2 and the 3, become the stoichiometric coefficients. So we need 3 of the vanadiums, we need 2 of the cobalts. That balances out. So at this point, we have 6 electrons in each half reaction. Our electrons are balanced. In a lot of questions, you're done. They might ask for what is the ratio of the vanadium species to cobalt species, oxidant to reductant, how many moles of one would you need if you were given another. So we're typically done in most questions if you're going forward. Want to be thorough here. So as mentioned, we're going to balance it in base. So we want to balance charges. I'm going to do it in base with OH minus. H plus would be the same thing but added to the opposite side. So we have to figure out total charge on each side of the equation, including all the molecules. Stoichiometric numbers are included. So on the left side, we have 3 VO pluses for net charge of +3. Cobalt hydroxide is neutral, so I'm going to ignore it. On the product side, the right side, we have 3 vanidates at -1 each, so -3, and 2 zeros. So that one's -3. So +3 does not equal -3. In order to get it equal, because I'm adding negatives, I want to add 6 negatives to the reactant side. So if I were to add in 6 OH minuses, the net charge would now be 6 minuses plus 3 pluses for a -3. Our charges are balanced. Okay, last step of the balancing process, consider the atoms. Fortunately for us, vanadium, there's 1 vanadium in each of the species, reactant product. There's 1 cobalt in each of the species, the reactant product. So it comes down to oxygens and hydrogens. So it looks easier to start with hydrogen because that's only on one side. You don't see it on the other. So on the reactant side, we have 6 H's from the hydroxides and 6 from the 2 cobalt trihydroxide. So altogether, we have 12 hydrogens on the reactant side. And then that also gives us 12 oxygens on that, plus the 3 of VO plus. So on the reactant side, we have 12 hydrogens and 15 oxygens. On the product side, we have no hydrogens and 9 oxygens, 3 species at 3 each. So again, on the left side, 12 and 15, 12 H's, 15 O's. Right side, no H's, 9 O's. That means we are short 12 H's and 6 O's, which should cry out to you 6 water, 6 H2O's. So to balance it out, we had 6 H2O's to the product side. Now we're going to have 15 hydrogens on each, or oxygens on each side, excuse me, and 12 H's on each side. So we've balanced atoms. And again, you don't want to go all the way to this step if you don't have to. You want to finish things off as quickly as you can. But in the event the question gave you answer choices that have the coefficients and the hydroxide or hydronium, depending on what they use, and waters in it, then we can count backwards. So and start at, are the atoms balanced? If the atoms aren't balanced, eliminate that answer choice. Then go to charges. Are the charges balanced on each side? If that's not the case, eliminate that one. Pretty much guarantee you will find the right answer at that point and you'll be done with it. But just in case, then you may have to do the third step, figure out what the ratio is, make sure the electrons are balanced. So balancing, it's kind of a pain, but it's systematic, and with a little bit of practice, it'll hopefully come back to you. Or in all honesty, if you had a GChem class where for some reason they rush through this, and I don't know why, but I've heard from students over the years, year in and year out, that it always seems to be electrochemistry that a GChem teacher will shortchange during their course. So make sure you can balance it. If you've never done it before, do a few more. Do a couple in the book. Okay, so let's go ahead and consider why we do this balancing. The two half reactions can ultimately be separated into cells, an anode and a cathode, and because electrons are being transferred, gained in one and lost in the other, you can create a pathway, a wire, where electrons will go from one cell to the other. Moving electrons equals energy. So because of the energetics of it, we have a whole subset of studying called the voltage, electrochemical potential. This is pretty typical from a GChem textbook, the half reactions. We usually write as reduction. Occasionally they might mix reduction and oxidation, but I'm going to go with the standard. Everything is measured relative to hydrogen. They arbitrarily assign H plus going to H2 gas a 0. And then anything that wants to be reduced more than H plus gets a positive number. Anything less gets a negative number. So one thing to make note of right away, because physics and chemistry have different conventions for sign. Chemistry always worries about the chemicals, the so-called system. Physics worries about what you can harness, the so-called surroundings. If you've ever learned whatever the system loses, the surroundings gains, or whatever the surroundings loses, the system gains, that means there's a sign convention issue. That's why in GChem, for a reaction that releases heat, the system is giving it away. Because we're looking at the system, we consider it a negative number. So negative delta G, negative delta H. Whereas in physics, that'd be a positive number. So voltages are positive for favorable reactions. So everything's relative to H. And the equation, delta G, the free energy, that's a GChem perspective, equals NFE, where F is the number of coulombs for 1 mole of electrons, N is the number of electrons in the balanced half reaction, and E is the so-called potential. So overall potential for either the half reaction or the full reaction. That's a voltage. Because of the sign convention, the negative sign is there. So how we apply it. You will likely get some sort of question, rank the reducing agents, the oxidizing agents, figure out how much voltage is associated with the reaction. Fairly straightforward questions. So in the text, I want to start with the easiest of questions and build up. So which is the strongest reducing agent? This actually, I'm going to use a table, so table 4.1 from the book, but you can also get this from a common sense or periodic trend perspective as well. But let's consider the table first and foremost. The strongest reducing agent is the one that most readily wants to be oxidized. And so the problem with this table, it's a reduction table like most are. Notice that in every entry, electrons are on the reactant side, not the product side, which means I need to go ahead and flip these backwards and see the most favorable reverse reaction. So strongest reducing agent, most favorable back reaction. So if I look at the table, I would consider Mn going backwards as being the most favorable, Mg being the most favorable, followed by Zn, Cu, Cl minus. But notice in the answer choices, they don't give us Cl minus, Cu, Zn, and Mg. They give us a couple in a different state, so you have to pay real close attention. Notice that Cl2 is on the reactant side, which means Cl2 is getting reduced, making it an oxidizing agent. You'll also notice that copper is on the product side. That makes it the reducing agent we want. Mg2 plus is on the reactant side, so it's an oxidizing agent. And then zinc is on the product side, so it's a reducing agent. So we can eliminate right away Cl2 and Mg2 plus because they are on the wrong side of the equation. They're not going to be reducing agents. They're going to be oxidizing agents. We're down to zinc and copper. The more favorable reverse reaction, so when I flip the number around, positive 0.76 for zinc, negative 0.34 for copper, zinc is your best reducing agent out of those species. You could do it in terms of periodic trends if you wanted to. And so reducing agents get oxidized. You know that Cl is a halogen, doesn't want to give up electrons, it wants to gain electrons. So Cl2 is not going to go to Cl2 plus. You probably could have gotten rid of that one. And Mg2 plus, it's already given away 2 electrons when it went from magnesium metal to Mg2 plus. It's not going to give any more away. It's already done giving off. So we could have gotten rid of those two from a common sense or periodic trends perspective. Between copper and zinc, probably needed the table, unless you have all these things memorized or you have properties of metals memorized, which most people don't. Table helped us. Okay, so scaling question up a little bit, which is the strongest oxidizing agent? This one's harder because I asked for things that are not in table 4.1. So the table is great. It's going to help us get through everything. But this one, there are no entries in table 4.1, so we have to do it from a different standpoint. This is a reiteration of what I just did earlier, the periodic trends approach. So every one of these species is positive, which means oxidizing agents get reduced. So we're looking at each of those cationic metals getting electrons and turning into, in most cases, a neutral metal. That's what I'm going to consider. So from a periodic trend standpoint, the first column, the alkali metals, and the second column, the alkaline earth metals, they want to lose electrons and become noble gases. So they're perfectly happy. Lithium plus, calcium 2 plus. We're going to assume that those are perfectly fine as is. So therefore, they're not going to get reduced. So I'm going to eliminate choices A and B because they're happy as cations. I'm down to 2 choices that are left, Pt2 plus and Zr2 plus. They are D block metals. They're both down a bit in the D block, 4th row, 5th row. So honestly, there's no way anybody, unless they are a PhD in chemistry and transition metals, would probably be able to just know off the top of their head. So how do I answer this? Well, you have to BS every now and then. Not that it's advised, but every now and then you have to tap into anything you know. And so here's what I'm going to use. Currency. If you have coins, metals that are considered precious, use them as jewelry, currency. If they've been a long-standing part of an economic foundation, that means they probably lasted. So gold, for instance, wants to stay as gold metal because if it oxidizes readily, your economy falls apart. You don't make coins out of sodium. First rainstorm, you discover it's a bad idea. So what I'm going to do is say, which is the more precious metal? Well, platinum, I think it's part of joy. I think we've heard of it as something in that nature. So probably pretty expensive. Zirconium, if you've heard of cubic zirconia, it's an artificial diamond. Typically, zirconium is much cheaper. So this is a stretch, but I'm going to go with the fact because platinum is a precious metal, it probably doesn't want to be 2 plus, it wants to be reduced. Otherwise, we wouldn't use it as a precious metal, something that we have a long-standing stable currency built on. It's a stretch, but if you don't have a table, you have to do something. Again, your approach, use the tools, use the information available to you as best you can. If you're given nothing, you have to scratch and claw for it. So I'm not happy saying the difference between C and D, but it's a learning tool. The purpose of this question, I'm going to assume on the MCAT they're going to give you the table. You're going to do it just like we did 4.4. I wanted to emphasize no table at first, so you sat there and had to struggle a little bit and come up with these things. My goal, my hope with this question, that you could get rid of A and B knowing they're happy as cations, and then you had to guess between C and D. That's a perfect thing. The valuable metal is just me justifying why I think C is better than D. And that's a skill in of itself that you develop. You want to get right answers for the right reasons, but every now and then you just want to get a right answer, and that's what this is. They'd probably give you the numbers, so let's go ahead and be sure with it. Here are the numbers if they were entered in table 4.1, and sure enough, Pt2 plus is the only positive one for being reduced, meaning P2 Pt2 plus is your strongest oxidizing agent. So this question, test skills question, developing the ability to attack questions on the test. Okay, EMF, very common thing. They want you to determine what the electromotive force is. Electromotive force is a voltage. So if I consider this reaction, I have to go back to that table again, table 4.1, and consider the half reactions. So copper and chromium are the two species involved, the two metals. So I'm going to take the copper entry and the cobalt or the chromium entry. So copper is a positive 0.34 when it's reduced. Chromium's a negative 0.73 when it's reduced. As written, chromium is being oxidized. Copper 2 plus is being reduced. So because of that, I need to reverse the chromium reactions from the table. And as you know, when you reverse a reaction, you change the sign. So go ahead and reverse it. So now I have chromium metal going to Cr3 plus. Its oxidation is a positive 0.73. The balancing, the stoichiometric coefficients, I need 2 chromium species, I need 3 copper species. The question early on when you take GChem is, do you multiply voltages? So you certainly multiply delta H, delta G, you multiply the chemistry terms. Always do, always should. This is a physics term. And so because its units are joules per coulomb, doesn't matter if you're getting that coulomb 2 electrons at a time, 3 electrons at a time, 1,000 electrons at a time. A coulomb is a fixed amount of energy. You do not multiply it by the number. That number is going to come into play when I convert to GChem. That's why it's a negative N Fe when determining delta G. But I don't multiply here. I just straight out add them. So you add the oxidation half reaction number to the reduction half reaction number. 0.34 plus 0.73 ends up being 1.07. Fairly straightforward to do this. Just the key things, remember to reverse the reaction and do not multiply voltages. So let's go ahead and apply it to the reaction. Again, I have to use the table from table 4.1, excuse me. You'll see that chloride, the reduction of chlorine into chloride is 1.36. The reduction of copper 2 plus into copper metal is 0.34. Again, have to look at the reaction. Chlorine is in the direction as written in the table, but copper is the opposite. So I'm going to have to reverse copper. So you'll probably not worry too much about balancing. Again, it really doesn't matter. It's just what happens to 2 half reactions. So the copper is actually being oxidized. So even though I've written as reduction, again, have to reverse it. It becomes a negative. And I just straight add those 2 voltages. So 1.36 for reduction plus a minus 0.34 for the oxidation adds up to 1.02, choice C. Just analyzing answer choices. You can pretty much bet the test writer is going to put in choices that if you do it wrong, then those numbers will be there. If you forgot to reverse the copper reaction and you were to add 1.36 to 0.34, sure enough, there's 1.70. Probably a good idea to figure out where some of the other numbers come from. Usually it's a case of you multiplied it by 2, so if we doubled the chloride reaction, we would have ended up with choice A if we would have apparently done that. If we would have mistakenly doubled the copper half reaction and subtracted it twice, we would end up with choice D. So answer choices, they take an effort, put in some time to make sure that they're answer choices that are tempting wrong answers. They're trying to get a certain amount of people to make wrong answers so that they get a bell curve. So follow the rules and look for common mistakes and don't make them. Last but not least, this question, what the heck is this doing in the middle of my GChem? So I just got done doing all this other stuff, and then there's a question like this. How much work? Work is a physics term. So to be honest, I look at this initially, and I freak out. I think most of us do. This is not NFE. It's not everything I'm used to. At least at face value, I don't think so. So one of the recommendations on anything on the MCAT you run into that you don't know what you're doing, look at units. You're going to hear this over and over in our class. In the books, you're going to read it over and over. It's just a survival technique on a standardized test. So a volt is defined as a joule per coulomb, and then we have 1 mole of electrons. So the units we have so far, joules per coulomb, and then number of electrons. The final answer is in the term joules. So I know the volts has to be in there in some way, and I somehow have to multiply joules by coulombs to get it just into joules. So the total number of coulombs and 1 mole of electron, we have to figure out how many coulombs you have. So we know from Faraday's constant that 1 mole of electrons the conversion is 96,500 coulombs per electron. So if we have 1 mole of electrons times 96,500, there's our coulomb number. So it ends up 1 mole of electrons times 96,500 coulombs per electron gives me the number of coulombs times joules per coulomb 1.6. The units all work out. It ends up power of 10 is the same in all the answer choices, 10 to the 5th. So I can ignore it and just worry about the mantissa part. So I'm going to go ahead and make 96,500 into 0.965. That's the 10 to the 5th component of the equation. So 0.965, and if you're wondering how the heck I did that, just move the dot over from behind the last zero of 96,500 5 times to the left, and it ends up sitting in front of the 9. So that'd be 10 to the 5th that I'd be multiplying it by. The key thing, it doesn't really matter even if you didn't do it that way, as long as you're having 0.965 or 9.65, something like that, times 1.6. 0.965 times 1.6, I have no idea what it is, but I do know 1 times 1.6 is 1.6, so this is a little less than 1.6. Best answer of the choices is 1.554. Again, 10 to the 5th, I don't care, because my goal, get a right answer, don't get a perfect answer. It ends up that energy converts. Work is a type of energy. It ends up the work associated with this simply equal delta G. So if you were to use the equation from GChem, delta G equals negative NFE, you would have come up with it. The negative sign goes away because, again, it's physics. So because that physics convention, the work is what you harness, so it's a negative of the free energy change. So a negative of negative NFE is just NFE. That's exactly what we plugged in. Number of electrons was 1. F is 96,500 coulombs per electron. E is 1.6. So the beautiful thing here is I panicked at first. I didn't fully know what I was doing. I thought work is a physics term. This is GChem. I went through a series of emotions and then calmed myself down to say, how do I solve when I'm not sure what I'm doing? Look at units. That was the trick in this case. The units work out, gave me the perfect answer. And then lo and behold, that's the way I was supposed to do it if I would have memorized equations. So your job, get right answers by whatever means you do. But make sure you can repeat the method, but getting right answers what matters. So in this video, we covered balancing. Hopefully you can do that on some of the homework passages. And then in addition, identifying the ratio of oxidant to reductant, that's important. And then finally, the voltages, NFE. In the next video, we're going to look more into electrochemical cells and applying this to figure out how we harness the voltage. But this, for now, is where we'll finish. I hope this is helping. Sincerely, I hope this is making the books go a lot more smoothly. I'm trying to explain things as we discuss it in class or as discussed in office hours, and hopefully it's making a difference. So again, thank you for using our books. I really appreciate it. Our company really appreciates it. It helps us to stay afloat. So part 2 is done. See you in part 3. Thanks.